All right, so as promised, we're actually going to go ahead and try to design one of these nice little deterministic machines that are going to play very nicely with this language of all possible decimal numbers. So earlier we were able to easily build a machine that made use of this epsilon secret transporter to nicely accommodate for the possible negative sign at the beginning of these strings. After that, we actually didn't make use of the epsilon transition, and it purely just became a game of our kind of classic non-deterministic structure in that, we go up across the top or we go down across the bottom, whether or not we have numbers before or after that particular decimal place. If we have numbers before and after the decimal, both paths are going to work, but we needed to be able to kind of distinguish between the two kind of weird outlier examples. Basically, how do we handle 0.2 and 4 dot? So we needed the two little branches. So if your initial question was just to try to design a machine right off the bat, maybe I gave this to you in one of our earlier activities when we only knew about deterministic machines. After enough kind of poking around, you might be able to come up with a machine that looks something like this. So this particular machine has 7 overall states, and I claim that this machine actually recognizes this language of all of these decimal numbers. It takes a little bit of unpacking, but if you go through it and kind of connect all of those little dots, you'll actually see the exact same strings are going to be accepted. That section across the top, that's all in black. What that's going to allow is it's going to require a negative sign. It then is going to have a number and possibly more in front of the decimal point. And then it can have as much stuff after the decimal point as it would ever want. So that's going to require negative numbers with at least one number before the decimal. So that's going to work really nicely with things like negative 13.37 or negative 4 dot or something like that. If you wanted to not have the negative, what you're going to need to do is you're just going to essentially jump across that little path from T0 to T2 on an initial read of just a number. So you can think about being at T2 as I for sure have something before the decimal point. Maybe that something is just a 1. Maybe that something is a negative and a 1. So we can kind of jump over state T1 and land us right at T2 on that kind of positive input. After that, it's the exact same rinse and repeat. The other portion of this machine then is then going to begin looking at how do we handle things like a negative 0.2 or just possibly a 0.2. Once we have one of those, then we'll make use of the kind of just jump across and see what happens. So if we went with the negative 0.2, you're going to come across from T0 to T1 on the negative. Then I'm going to read a dot right away. So I'm actually going to come down to T4. What I need to do is I need to have a number after that because I know I didn't have anything before the decimal. So I'm going to move across on a number to guarantee a movement and then do whatever you want to after that. I really don't care. Have as many extra numbers as you would ever want. Same exact structure is going to happen on coming out of T0 if I don't have the negative. It's just going to jump to T4 right away and then require another number afterwards. So T5 is going to be where most things are essentially going to land, is that if you have numbers before or after the decimal, a lot of those things are going to be ending up down in the T5 world, which is kind of where you think most of your kind of classic numbers are going to emerge. If you ever encounter an extra decimal after you've seen the decimal, then you're going to go right down into this trash can at the very bottom of the screen and then just sit and spin on that. So I was super lazy and I just wrote any. You can think about this as like a star, and that any extra input at that point in time, you're never getting back out because you had 2 decimal points and you've broken some things. So that was kind of sculpting it just as a thing on its own, not making use of already building this thing in an epsilon transition world. Once we know the epsilon transition one, you can actually use this structure to build another deterministic machine. And we're going to see that they're actually the same as this machine up above. So if we were to play that little game that we had before of where are we going to be and where could we potentially be upon some read, you would end up with something like this. So I'll go through a couple of the steps and then I'll kind of let you just explore it on your own. So right off the bat, when you come into this machine, you could be sitting at S0 or you could be sitting at S1 if you take the teleporter across. So you effectively can think about this machine as having 2 starting places. It starts at S0 or it starts at S1. take your pick. I don't care. It's obviously going to be required if you start with a negative, and that you only have to start at S naught because you still have to read that negative, and nowhere else can you have a negative. But from the initial onset, there's only 2 spots that you could potentially start at, S naught or S1. So that's going to become my initial label for my deterministic machine. So if I'm at S naught or S1, and if I read a negative, well, the only place I can go after that is actually be in S1. So I had the potential of 2 initial starting places. Well, if I started at S1 and I read a negative, I'm dead. So that one doesn't work at all. So it says, nope, you had to start at S naught, and then you read the negative, so then you move to S1. So that's what's happening there. If I was at S naught or S1 and I read a number, well, if I was at S naught and I read a number, it's going to say, nope, you should have taken the teleporter. And if I was at S1 and I read a number, I can either sit at S1 or I can go down to S4. So that's why I get this little arc, and then I'm going to go into that little spot. So it's my possibilities of S1 or S4. If I'm at S1 or S4, and if I read a number, well, if I was at S1 and I read a number, I can sit still, or I can move up to S4. And if I was at S4 and I read a number, well, then I shouldn't have gone to S4. I got there premature. So that means if I'm at S1 or S4 and I read a number, I should have stayed, and then I have the potential to go to S1 or S4, which is why we're going to spin on that thing. That's some of the weird ones that can occur. So I can sit on S1 or S4. Basically, each time I have a number, I'm going to try to go down the S4 path, but I might not be successful. It's exactly that idea when I had, something like 13.37. When I started, I took the secret teleporter. I could spin, and then go across on the dot. Or I could have spun, come down, and then go across on the dot. Or if I were to come down initially, then I would die because I can't leave S4. But you can see that I could have been at S1 or at S4. So it's this kind of nice little processing to kind of go back on some of the numbers that we've already seen. So that's why we're going to sit and spin on that particular one. If I was at S1 or if I was at S4 and I read a dot, well, then we're going to move across. So that's where I'd go to S2, or I'd possibly go to S3, which is exactly that thing. So if I'm at S2, or if I'm at S3, and I read a number, well, S2 on a number is going to send me to S3. S3 on a number is going to keep me there. So if I have a number, I'm just going to go down to this state S3, which is kind of I have numbers before the decimal, and I have numbers after the decimal now. If I'm at S3 and I read a number, I'm going to sit there indefinitely. And in all of the other scenarios, if I read a decimal after that now, so you're going to see that I'm going to have to go and die on some decimal reads, because once I've passed the decimal point, then I have no hope to kind of be successful, is that I've already had my decimal and I can't have any more. So that's the kind of outer bit. The inner bit would then be if I read a decimal really early. So if I was at S0 or S1 and I read a decimal, well, it's going to tell me that I had to be at S1, and I read the decimal and it sends me to S2. If I was at S1 and I read a decimal, it's going to send me to S2. So that's where those 2 paths are going to come into play. And then if you're at S2 and you read a number, it's going to send you over to S3, which is exactly what that structure does. So if you sit and stare at that one long enough, you can see that we ran that cute little processing of basically take the machine up above and then convert it into this deterministic structure. And if you then go back to the one that maybe we were clever enough about designing before, you can see that it's going to look very, very similar. And that I lied to you in that this is actually not a deterministic machine. So there's one small issue with this one, which is that piece right here should not have a loop. So I lied to you in the beginning, but I will change it right now, and I'll change it in the notes, because you can see that that has a non-deterministic structure, and that I'm actually leaving on zeros in 2 different places, and that I should not be spinning up across the top. So I built the little machine that allowed it to, and I should have come down on it. So anyway, if I come down afterwards, that's great and dandy, and then we can play with that. So that allows for, if I have a number afterward, then I go down, but I do need this one to be accepting because maybe I don't have a number after the decimal. Something like a 4 dot would need to be accepted up there. So I apologize for making that thing appear to be, well, claiming that it was deterministic when it was in fact not. But if you erase that little bit, that machine should hopefully look identical to the machine that we built here. Here I did not have the loops, I was correct on that one. And then I just relabeled them up above to make another machine actually work. So again, that same little game that we played before is that anytime you have one of these weird little non-deterministic machines, even if you add in this epsilon transition, you can always convert this thing into a deterministic machine, which actually leads us to kind of our nice little theorem statement, is that anytime you have a language recognized by one of these non-deterministic machines with a potential epsilon transition, you can actually construct a deterministic machine for that exact same language. This is an if and only if statement, so it goes both ways. The other direction is actually kind of silly. So if you have a language recognized by a deterministic machine, it's also recognized by a non-deterministic machine, in that all deterministic machines are also non-deterministic, in that it's harder to be deterministic actually. So what you get is you get this kind of cute little connection between all of these things. So deterministic, non-deterministic, and non-deterministic with epsilon transitions are all connected. They all give rise to the exact same types of languages, and all of this is going to connect into what are referred to as regular expressions. So we're going to have these regular languages that are going to then be built out of regular expressions, which are things that you've probably heard of, at least maybe glimpses in the back of your head. So we're going to hit that world really, really hard. Before we jump into a couple more examples, I should allude to the kind of weird scenario that I mentioned at the very, very beginning, which is that our original machine would have rejected something like the number 42 because it didn't have a decimal point in it. So if you wanted to fix that, what you could do is you could create one additional transition that skips the decimal places all around and then jumps into state S3. And then it would allow for numbers like 42 to be totally fine, in that it would work without ever having to see a decimal point. It would also work with things like negative 42, but the epsilon transition already did that. So you have this kind of three-way trident, I guess, is that you have a decimal with some numbers before, decimal with some numbers afterwards, and then possibly no decimal